Okay, can everybody see my graduate student community slide?
Perfect.
Okay. All right. Thanks, Kevin, for joining today. This is Galilee College of Engineering graduate student community. My name is Jason Beatty. I am the presenter for Kevin Weiss. There we go. All right. Here's our pretty much our organization chart. You could say, Kevin, that you definitely understand that word from Air Force. Co-chairs, they introduced themselves earlier today, and then Stephanie, he just introduced himself too. Then we got several other people. You can see I'm just kind of the support. Definitely just here, most likely my last semester, Kevin, as I should be defending my thesis in the April. You have everyone else, and then of course Farouk is our pretty much our mentor from the faculty. Every Friday we meet at 4 p.m. Now we started to kind of do a Zoom thing. We still meet in a location, and it'll come up in a later slide too. But this is a meeting we have every Friday at 4 p.m. Just we get together and we discuss the things we're talking about. All the different speakers we're going to have, the lightning talks, and everything else that we do in the GSC. Here's a little thing to help people. If you're new to this, you haven't been to one of these speaker events with the GSC, you can take a picture of this, or so you can get some links and stuff. Of course, our LinkedIn ID also. We have a Facebook too that we keep up. Help spread the word for GSC. Really helps spread, and it's not just Mechanical College of Engineering. Any graduate student can join us. And we've had a couple of different ones, even from I believe writing graduate student from the writing college or something like that came to one of our meetings one time. We enjoy it. It's just a graduate student help a network of graduate students just to help anybody that may need some help here and there in graduate college. Again, we have a YouTube area too. And Kevin, your video today will be posted online after this. This is where we meet physically, and this is our room that's actually dedicated to us. It can be used for anything we want to have a meeting at, but we meet here every Friday too. A few of us usually meet in person and then connect via Zoom to the rest of the people. Please remember to sign in via Google from the link in chat. Appreciate that. Just get your information so we can bug you that, hey, join us. Really just helps us. And of course, today presenting is Kevin Weiss. All right, Kevin, your turn.
All right. Let me see if I can figure out how to do this. All right. Can you guys see my slide?
Yeah.
All right. I'm going to get started. So this one, I don't know, it might be a little bit different than some of the other ones you've been listening to. I was just going to go over what I know. So I'm required to give a disclaimer since I'm going to be talking some Air Force and Department of Defense things that happen on bases. But these views in this seminar are my personal views and do not necessarily represent the opinions of the U.S. Air Force or the Department of Defense. Sorry, did someone say something? All right, moving on. So the agenda here, I'm going to do a brief introduction, talk about what it's like working for the Air Force, just some of the nuts and bolts, and then I'm going to go over some lessons learned from my own personal experience working here, and then I'll go over one of the main areas that I've been, I guess you can say, researching in, and that is risk management. And then if we have time, question and answers. So I'm going to start off the Air Force is sometimes a dangerous place. this is a place where we build things to destroy things, and we've got bombs, guns, nukes, all kinds of things, including parking lots. Let me explain the parking lots. Well, a few years ago, I was arriving to work and getting out of my car, and I went to go cross the street. It was kind of dark, and it's kind of like at OU when you cross the street on a crosswalk, people stop for you, and the first car stopped. So I started to cross the street, but there was a guy behind that car. He just loved work so much that he decided to swing around the guy and take off and nearly run me over. Like, saw my life flash before my eyes as I look to see who's driving this car. None other than Mr. Beatty. True story. He was my intern. Anyway, so some good, just basic things about the Air Force as a civilian, if you ever consider it. The pay's reasonably well, like for an engineer who can accomplish just basic work, he's got a little bit of experience, pays usually between 88,000 and 137. And if you get really good at what you do, maybe all the way up to like 160. Federal government still offers a retirement, like a pension. It's not like a pension you can completely live off, but it's still a decent amount. And they also do like a 401k. Leave was one of the things that kind of convinced me to start there. Is you start off with 13 days vacation every year, and after 3 years, you get 20 days. That's like a whole month. So it's a pretty good deal. And after a lot more years, you get 26, and then you always get 13 extra days to use the sick leave. Another kind of advantage, if you do get a job in the Air Force, there's lots of different jobs. So if you start a job and you get really good at it or you get bored with it, there are more jobs you can transfer into. There's also, maybe if you don't like staying in the same place, there's worldwide locations. We have bases from Italy, Germany, Japan. In fact, right now when I'm giving this briefing, I'm in England right now at a base working a project. And then we have, pretty good job secured. Oh, maybe we'll have to subtract job security from the last couple weeks. All right. To go over some of the jobs that I had and the high level what I did there. I started off at Tinker Air Force Base, designing industrial shops. I'm doing the technical, how we're going to build the shops. After that, I transferred to a job at Ramstein Air Base in Germany, and I worked there a little over 3 years, going through all, kind of like working as a city engineer for a base, going through things that are breaking down, coming up with 5-year plans to fix the base, and just that kind of work. It was a kind of neat to live there. And then I came back when the Tinker Air Force Base acquired the GM plant. I know me and including Mr. Brady worked on fitting that out, so it would be industrial aerospace shops. For work there at that same job, and eventually got promoted to be the supervisor of the engineering office. So get more responsibility. I then started kind of getting a little bored with that job, so I started looking around, and I saw a job that was called Airfield Protection Research Engineer. And I took a job at Tyndall Air Force Base in Florida. It's sometimes called blast engineering. That's where we be looking at new materials or new methods to help protect infrastructure and people from military type threat loads. And then my most recent job is working for the Air Force Civil Engineering Center. It's kind of like a headquarters location, and I do the structural engineering. They call it subject matter expert, even though that's just the title. All right. That's enough about me. Let's go over some just lessons learned from my career here. And so one of the first things, I know most of you at least are likely young engineers getting out there. And one of the things that's important to know is when you're starting, you probably don't actually know that much. And that's completely okay. And the people you're working for are going to know that because they were also starting at one time. In fact, to go over my first project I remember getting as a young engineer, I mean, I had great ambitions. I had just finished like 130 hours at the other Oklahoma university and got this project, and it was to install an eye wash. I mean, like the thing you in the chemical lab keep clean your eyes. Well, not even the eye wash shower. And it was like, really, this is what I'm going to do. And then, I was kind of disheartened by that. But then even worse, I didn't even know how to do it. A simple project like that. And it was kind of embarrassing. I didn't know what to do. But my supervisor at the time, he's like, hey, you need to get with this guy, Elijah Straw. Have him take you out there and he can show you what to do. So we walk out to the job site where it was going to be. He goes, tie into the pipe here, run this size of pipe, put hangers, this kind of hangers, and then bolt it to the floor like this. And I was like, okay, so I'm just going to write that down. And I got back, talked to my boss, and I was like, hey, I don't understand. Like, the guy who's going to do the work just told me what he's going to do, and I'm going to write that down. And then, he kind of explained, well, this is a first project, and then there are important parts because it's a big system, and you need to be able to communicate and write down what needs to get done so everybody can follow the same plan. And the other thing, I put it on my slide here, when you're starting out, only a fool would give an unproven person something important. So when you're starting out, you might get some really piddly jobs, but take them seriously and learn on them. And then also, it's okay to not know what you're doing at first, but definitely don't stay that way. Learn how to do the job you're doing and get smarter at it. Okay, another important thing that I come across particularly often where I work now is learn what's already out there. Before you're going to patent your next brilliant disruptive idea, check to see what's out there. I got a story of fairly recently. Is this really smart guy came up to me, and I mean, he is 10 times smarter than me. He has a PhD in chemical engineering, reads all the time, his lots of stuff. But he came and he's like, Kevin, I've got this white paper I wrote, and I want to think about developing some concrete that can set to 8,000 psi in one day. And he had done some preliminary work on it. He was all excited. He wanted me to fund the project with my funds. And concrete repair is a big deal to the Air Force because sometimes we're worried about people making a bunch of holes in our airfields, and we need to be able to repair them quickly to get our delicate multi-million-dollar planes off the ground. And having concrete set fast is nice. The only problem is, if I wanted 8,000 psi concrete that sets at that level in one day, I can just call the cement plant and they can send it right now. It's already available. And so this guy, even though he was really smart, he had missed some stuff that was already out there. So another thing I got here is, read. It's very important to read. You guys probably being graduate students are already somewhat familiar with this, but read not just research papers, but read specification, design guides, design codes. There's a lot of stuff out there. In fact, I remember in 2002, I was taking a concrete class, and this guy, he was probably in his mid-70s, he came up there and he brought his concrete book that he had learned on, and it was 30 or 40 pages, and he was like, this is all you need, and this new code book's got 200 pages, and it's not all that. It's just a bunch of extra stuff you don't need. And there is maybe some time to talk about there being extra stuff, but as an engineer doing that type of work, you should know all of the stuff that's in there that's been developed. In fact, the current code book for the same concrete stuff is now 700 pages, and we don't even print it out. It's so big. The last part on knowing what's out there is don't be afraid to talk to people who are going to be building your ideas. The fact is they actually may be smarter than you at what we're doing. And I know it can be hard, or maybe you think that they're as smart as they are, but they really are. There was a guy I worked with, his name was John T. And when I was first starting, he was building this crane system for me. And I just thought to ask him, well, how do you know where to put the columns? Because, I draw them on my plan, and they're, it's easy to make things at right angles and distances. And I was like, well, how do you keep it all square? And he went on to tell me one of the most complicated, precise ways of using strings and all kinds of field equipment and math to get it done. I was actually shocked, but he was brilliant at doing that. In fact, I even needed to use that one time about 20 years later when we were on a project working on an island somewhere. And last verse on this one is be careful out there, because people are going to think based on your title, being an engineer, being a PhD, that you are incredibly smart, which you are, but don't let that go to your head. And, just keep that in mind. You can also burn your free respect by being wrong with those people who actually know the right answer. Right. Another important career point is, you need to learn how to figure out how to solve problems. If you can figure out how to solve problems and do it successfully, you will be very valuable to your employer, and your reputation will grow, and it's just a great thing. And let me give you an example of a project that I started. It was installed about 500 horsepower, high pressure industrial air compressor, high flow industrial air compressor, about $1 million piece of equipment. And my boss had designed it, but he gave me the responsibility to do the field install. And I didn't think too much of it, but go out there, verify everything's installed like the plans say, and we go to turn it on for the first time. We turn this thing on, and within seconds, the whole building is shaking. And when I say shaking, I don't mean like little vibrations. I mean the wall was moving enough you could see it. And so we quickly shut it off. And the guy who had sold us the equipment, he was there at this time, and he went on to tell us about 10 things we had done wrong. I mean, he didn't think to tell them before we did this, but he came up with, we didn't attach the equipment to the base strong enough, and lots of other things. So I went and, instructed people to do what he said, and we remounted it. We poured a bunch of concrete into the base to try to weight it down, and we went and turned it on again, and there was no difference. Same thing. Kicked it on, building shakes. Got to shut it off. And this was a very important air compressor, because it was a one-of-a-kind Air Force thing. It was redundant, that had to run at all times, or that mission would shut down. And the old compressor was next to it, and it was limping by and could go down at any time at this point while we're trying to get this done. So there's a lot of pressure to figure this out. And so I did. I called anybody else I could think of, an expert into it. I talked to them. I got their advice, and some things came up. The ones I remember are, we got to mount it to the building stiffer. We need to put a rubber isolator between the piping and the compressor. And we did all these things again. I did what all the experts had told me, turned it on, no difference. I was getting very stressed. And this is now like 2 weeks, because it took like a week to implement all these things. So then I started reading. So I went reading any book I can find about vibrating equipment. What could cause this? And I found an actually old book from the 50s made by a Kellogg company. And they had a simple explanation, still technical, but it talked about, vibration and the fluid vibrating the pipe. The whole time we had been thinking that the vibration was traveling from the equipment into the ground, into the foundation. But what it actually was doing is it was the pulsating air. It was a reciprocating compressor, was shaking the building. So there was no way to decouple the pipe from that. And so what I had to do was we had to make as short as run as possible of the pipe, run it into a large enough tank to take out those pulses. And in between that tank, had to build the monstrosity of a pipe support to hold it. And I remember my coworker, Stan Loring, telling me, he's like, if you make them build this giant pipe support monstrosity, it doesn't work, you're done. And he's probably right, but we turned it on and it worked. And the point of that is just, you're going to face some problems. You're going to need to work through them. And if you can work through them and solve problems, people will take note, and that'll work out for you. And the last one here is not exactly technical, but it's very important. And it's important to learn how to work with people. I had a boss one time, I don't know if it's good or not, his name was Mike Lee, and he told me, you need to read this book, How to Win Friends and Influence People. You should always question when someone knows you and tells you to read this book. But I don't know you guys, so it doesn't matter. But I would encourage you to read this book. It was written in the 30s by Andrew Carnegie, and it is very applicable to today and all times of just how to work with people. And I learned a lot from reading this. Also, something I'm sure a lot of you should realize is you're all very smart, and you've been in a learning environment where you've been doing analytical systems of some kind. And that's not exactly how everything works out there. So be aware that people don't work like analytical systems. And you should study this like any other problem and work at it. All right. Now we're going to move on to my technical part. And I do apologize. This one may be a little boring. A lot of my more interesting projects are all not public releasable, but this one's one that we can talk about. And we're going to talk about risk and how do we manage risk from a, we'll say, high company value, or in our case, the whole DoD, and that's Department of Defense. So I got this picture on the left here. This is a building in East London called the Ronin Point. What happened was back in May of 1968, they had just completed this structure, and this was a precast building where a bunch of precast panels are set into place, tied together with some small components and stacked up. Well, about 2 months after it was inhabited, an old lady went in to make some tea. And as she was making her tea, she turned on her stove, but the pilot light wasn't lit. So she left to go get a match, and when she came back and lit it, it deflagrated and it made a small explosion. I say small. It did not kill this lady. It knocked her down into the next room, but it created a small pressure wave which blew the wall panel out on the 18th floor. Well, after the wall panel blew out, there was nothing holding the floor above it together or up in the air anymore, and so that floor fell down, 9-10 feet, and hit the floor below it. And once it hit that floor, that had released enough energy that it broke the wall completely out of that one, and then it progressively collapsed and took out this whole corner of the building. And there were 4 people that were in this building, or the part that fell apart, that did perish. And this kind of started at least the concept of progressive or disproportionate collapse. I got a few more examples of disproportionate or progressive collapse. One you guys are all, I'm sure, familiar with, being from Oklahoma, is the Murrah building. This was a large blast that was set right by the building, and this blast blew out some columns and a transfer girder, and a large portion of the building collapsed, and that was deemed a progressive collapse. Another one that happened shortly after that in 1996 was Khobar Towers. This was a military facility, and similar, they had a blast that it was far enough away that you would have thought the building would be fine, but it knocked some of the supporting walls out on the first floor, and then all the walls above that collapsed, and a relatively small collapse progressed into something bigger. And I got another picture here. It's a little more recent. This is the Surfside condominium in South Florida, where a pool deck collapsed from some, let's call it degradation, overloading, and the pool collapsing weakened a column, and after a few minutes, a column collapsed. The center part of the building collapsed, and about 7 seconds later, the side of the building collapsed on top of that, but the other side was left intact. So that's another example of some progressive collapse. So we're all engineers, and how are we going to solve this problem? This was what some people came up with in the 90s and in the 60s. After Ronin Point, the British put in their design codes that you need to put a nominal amount of some reinforcement that forces you to tie all of the structure together, even if you structurally don't need it to. This would have, solved the Ronin Point by not letting that wall get blown out, because it just didn't have very much connecting it laterally to the building. Well, after the Kobar Towers incidents, the Department of Defense developed Unified Facilities Criteria 4-023-03, which is design of buildings to resist pressure collapse. And then finally, recently, the American Society of Civil Engineers developed GSC 76, Standard for Mitigation of Disproportionate Collapse. What are we technically doing in this solutions? Well, for the DoD, we put this criteria that said for all buildings 3 or more stories, you need to explicitly design to resist progressive collapse. Well, and how do we do that? And one of the simplest to explain ways is we're going to remove an important part of the building in the design phase, like a column. That is, we're going to pull that column out, and the damage cannot spread to other members of the building. So you can kind of think, well, probably the way that's done is, okay, well, I just need to make my beams really strong then, because now if I pull out one column, the beam now has to span, so the beam needs to be stronger. Well, that sounds simple, but that even adds an unintended consequence to our seismic areas, because one of the things we're worried about in seismic is for our columns to bend and yield. We don't, as the earthquake's going, we don't want our columns to yield. We want the beams to yield so that all the energy absorbing is happening in the beams, and then our columns remain relatively straight after the earthquake. Oh, well, there you can see like maybe a conflict. I've got one area where the goal is to make the beams stronger, and one area where we are intentionally a lot of times making the beams weaker. Now the solutions will eventually converge, but it's still a rough solution. So this brings us to the question: well, is this even a good solution? Well, some things to point out here is, well, the design analysis to do this is difficult and expensive. I think you guys know, but buildings we don't really prototype. We're going to have to design a building, and it's the one building that's going to be built like that, and we have to prove that it's going to work via analysis. Well, that can be difficult as you start to do with complex things like removing important pieces of the structure and figuring out how the structure is really going to behave. And not everyone's going to agree with the method. Also, construction work gets very expensive. I'm sure you've heard rumors, and they are true sometimes, that engineers design things that cannot exist in space-time. What I mean by that is, okay, I've got to have this reinforcement. It's got to go continuously through the column, and it can't have joints, and then it's going in all directions. How do I even put that together? Like, it's physically difficult, if not impossible, sometimes to put together. And then we need to talk about the initiating event. What I mean by that is, like, for the Murrah building, that would be like the bomb going off. And I kind of mentioned, I was saying, hey, our design method is to remove one building column. Well, what if the bomb takes out 2 columns? Well, GSC 76 has a solution for that. It's called Collapse Design Category D. And they're like, well, now not only do you have to survive 2 columns, one column you have to survive 2. It's like, okay, well, what if the terrorist drives into the garage under the building and parks it between 4 columns and it knocks out 4 columns? Okay, well, that's bad too. And then finally, what if the beam that we're hoping will span this is also damaged in the initiating events? Okay, so this brings the question, well, if we're using these methods, how much risk are we really mitigating? So I'm going to point out one research paper that I think is really well written, and it's called Progressive Collapse of the Murrah Building Revisited. And surprisingly, this paper was written in China by these Chinese students. I kind of found that surprising that the Chinese are taking our data and our information and developing their building codes and stuff. But I will say this is a very impressive analysis. They took a full simulation modeling from the blast initiation, running that through a hydrocode to push out the forces onto the building, and then using a dynamic nonlinear analysis on the building, see how all of the building performs. Well, I mean, that's really hard, but you might say, well, how do they know that's right? Well, they did field testing with some of the critical part of the setup here, like the bottom floors. And then they ran their simulations and adjusted the simulations until the design as it was designed and built in the 70s failed like the bomb blast from 1994 at the design bomb that happened. So they did a very good job. Well, one of the picture over here is kind of showing, okay, well, I remember going to the Murrow Building Museum, and there's like a video, and they were talking about the bottom reinforcement on the transfer girder was hooked into the column instead of continuous through the column. They were saying, well, if the rebar was continuous through the column, the collapse wouldn't have been as bad. Okay, well, this guy is looking at something more substantial than just the continuous rebar, but they're looking at seismic detailing and how well it performed. And the picture I showed here was kind of the best one of their group. But I don't know if you can notice, it's better, but it's still damaged. And if we would have put the cost of progressive collapse into this, would it have been the right decision? And this is an important one because this building collapse is what a lot of the justification has been made on. Okay, so this brings to the question that we're currently working in the DoD is, can we move to risk-based? And I heard from you guys that told me who you were. That may not be familiar with how we do building loads. Well, the simple explanation is we take a statistically predicted design load that we know has some specific probability of failure. That's kind of how we look at it. And then for more important buildings, we accept a lower probability of failure. So that's how we decide what wind speed to design a building to and what seismic loads to design a building to. Well, so how do we apply this to progressive collapse? In ASC 76, which is the new code, they have a chapter called risk assessment. So let's see, does it solve this problem? Well, here's kind of what's in ASC 76, and we've got this risk equation, which is hazard likelihood times the vulnerability times consequences that equals your risk. That looks like a good risk equation. So how do I apply this in the real world? Well, I've got this hazard likelihood. This is how likely are we to have a progressive collapse initiating event. And I don't know what all they were thinking of when they were making this table, but some of these, we've got a terrace bomb like 10% in 50 years. Hopefully not. Anyway, then they've got this thing called vulnerability, and it's defined as limited, moderate, or significant. Also kind of tough there to know what that means. And then we've got consequences. I mean, these are probably the easiest to define of the three things, but it's still very vague. And when we're trying to tie in, like, when do we apply progressive collapse and how much design do we pull one column out or two columns out? This is kind of not developed all the way. So another research paper that's out there is The Likelihood of Progressive Collapse from Terrorist Attacks by Mark Stewart and Matthew Grant. And these guys went through kind of starting the risk-based process and looking at, well, how likely is it for a building to collapse in a progressive manner? And how important is that? And they've kind of gone through these tables. I encourage you, if you're interested in this topic, to read this paper. But the gist of what they came up with is it never makes sense from a financial or a societal perspective to try to prevent progressive collapse explicitly. Or they're not saying, you shouldn't use good design principles, but going to the trouble of saying, a column got knocked out of my building is, maybe there's some cases where it doesn't make sense. Right. So where are we going with this at the DoD? Well, this is an active work in progress. We're talking about, because right now, I think if you remember, I mentioned that we apply this for all buildings 3 or more stories. But that's a big cost, and I'm sure everyone's aware of the government. We don't want to be spending money on things we don't have to. However, if you've ever been on a code committee and you've tried to add things in a consensus decision, it's difficult. Now, trying to add something that's discussing potentially increasing risk, this is definitely, like, at least in our area, like new ground, because trying to quantify that, yes, it's increasing risk, but it's still increasing it at the infinitesimal level. It's a tough discussion to have, and a lot of people don't want to make that decision. They're much easier to say, well, we're just going to lower our risk, always lower our risk. So anyway, I don't know exactly where this is going from this, but I thought I would share, kind of a technical problem that we're dealing with. So that was progressive collapse. I've got one more thing in risk management, which is airbase protection. So I just kind of posed a few questions here. And like I said, I can't talk a whole lot about the details on this, but I can kind of talk some of the big points where we're doing research, what we call research anyway. Maybe not the exact same thing as you guys call research, but and that is there any difference that a military base faces than any other piece of built infrastructure? Well, I can tell you it's not entirely clear what the difference is. Some questions to ask is everything on a base a potential target? So what I'm talking here is the difference. Are we worried about people intentionally trying to destroy our stuff? Our base has a childcare center on it. Is the childcare center on the target list of our enemies that we need to protect, or are they going to pass that over? And then if we find out they're passing it over, are we going to stick a GPS jammer on top of it? Or, these are things going on. Not saying we're doing that, obviously, but thoughts. And then what do I protect against, if anything? There's some people out there that are like, well, you can't, modern weapons have advanced so far, you can't protect against anything. So you don't do anything. But then it's like, well, you just left the $100 million plane out in the open. Is that really better than nothing? Or anyway, and then how do I decide how much risk is okay to accept? It's difficult. And then how do I reduce risk to these military threats? How do I quantify the deterrence that my risk prevention is going? And what I mean by that is, let's say we build a bunch of really hard targets, and now the adversary is looking at that as like, hey, I can't knock out these targets, so now I'm gonna not attack. Well, how did we know they didn't do? How do we know that's what happened, that they didn't attack? And then another one is, well, threats change every few years. There's lots of technology movement, but infrastructure takes years to build, if not decades. Can we ever do our investments right? And then how do I quantify risk in an accurate way? So if you're interested in this topic, a good starting point, there is some public information out there. And one is this paper, Concrete Sky Airbase Hardening in the Western Pacific. You don't even have to have a university account to read it, but these guys, I've met Mr. Walton before. He's very, very good and knowledgeable, and he's kind of talking about some of these risk concepts. Right. Well, I appreciate you letting me come speak to you guys, and I hope you enjoyed this. Do you have any questions? I guess I'm turning it back over to Mr. Beatty.
Jason, I think your audio's out again. But while Jason's getting that set up again, I just want to say thank you. And it definitely wasn't boring, like you said you're worried about.
Well, I have more interesting things, like I can show stuff blowing up and how blast response is, but everything I could find video like that, it was like, it's not that it's classified, but I can't put it in a public forum.
That's fair. I was wondering if you have any, if you're allowed to talk about it, any sets of buildings that are like intentionally receive like the highest level of risk, like no matter what, just based on location or anything like that, like Andrews Air Force Base or something, like coastal, big population Air Force bases or government buildings.
I heard Jason now. So help me understand the question a little better. You said, are there places we have bigger risks from threats, or we create
Or
bigger risks to other people?
You just assigned a bigger risk to it, like just based on location or the surrounding area.
Yeah, definitely. And the part I was talking about, the hard part is always quantifying that.
Right.
And how you're going to, because generally, you're talking millions, if not billions of dollars sometimes. Yeah. How do you make sure you did the decision right? There's definitely research that goes on in that area. So
Thank you. All right. I just want to say thanks again. I actually have to leave for another meeting, but I think Jason's audio is back.
Okay.
Thank you, Brad.
Hopefully.
I have a question.
Go ahead.
Sure. So I think one thing I was thinking is that has it ever happened that you have thought of a solution and you've worked on it, and then you had some snag while implementing it during like actual structure building, and then you realize, oh, we need to make a change, and then like you're almost halfway in it. So have you come across anything like that? And if you have not, then how do you like preemptively sort of think about a plan B instead of a plan A, let's say?
Well, so I definitely like focusing the most energy on the plan A
Right.
until I have to come up with plan B. Definitely things have happened that I mean, Jason can talk some of these too, where we've built half a building, and then maybe it took a while to build, and some things have changed, and the customer's like, "Oh, I need to change how you're going to do this." I mean,
Right.
it happens.
Yeah.
And we just address it. I mean, when you're doing your designs, anytime you can make it as flexible
Right.
as possible is good, but you don't want to be wasting money either. It's kind of
Right.
kind of a hard balance sometimes.
Mhm.
I don't know if I'm answering your question that well.
No. It's perfectly fine because the idea is that, like, obviously we simulate and we sort of try to consider everything. But again, since you do implementation and like you do make it in a physical world, I just wanted to know if you had an instance where it's like, okay, you did it, but feels like, as you said, it took more time and things got added on, or certain things changed, certain design considerations changed, and then you had to like do something in the middle. And then I'm like, as a designer, like, how do you sort of consider those things? That was my question.
Okay, so you try to know your customer, who you're building it for, but to add on to this, it's probably more common with the stuff I've worked on that we've spent too much time trying to do that.
Right.
Because we mitigated a lot of things that never happened.
Gotcha.
We talked about it, and also I kind of implied it in my answer that if you start, the longer you take to get something done, the more likely you are to have a change to it.
Right.
If you want to compress that schedule as much as you can because if you piddle around, you design a whole building, but you don't start it for a couple years. You got a new customer, and they're like, "Oh, I need you to redesign it."
Gotcha. Yeah. Makes
So
sense.
don't spend too much time thinking. You always hear like it's an 80% solution is kind of the target. I don't.
Gotcha. Makes sense. Thank you.
Just my opinions, though.
Oh yeah, absolutely. Thank you so much.
Welcome.
So I have a comment for Kevin.
Yes, sir.
In our laboratory, we are putting together a dynamic planning system
Mhm.
for policy. So what you're talking about really is policy. How do I fix this? How do I do that? How do I take this risk into account? Stuff like that.
Yes.
And so what we are looking for, what we are working on is putting together a system from the cyber physical social perspective. That is not just cyber physical. And let me tell you why. Pre-pandemic, the Tinker Air Force Base had a supply network that was lean but very fragile. It only took into account cost and time. And during the pandemic, the suppliers were let go. And post-pandemic, they had to come back. So the social aspect was not taken into account. So the first thing that we're doing is we're taking into account cyber physical social. So the social part is very important. And then what we want to do, you talked about minimizing risk. There's another way of minimizing risk. The way you're talking about is mitigating risk. It's risk mitigation. That means the implication is that you make the models as perfect as possible, but you'll never get them perfect, so there's always going to be some risk. The alternative approach is anchored in the work of Herbert Simon and Taguchi, where the basic notion is that you manage risk. There's a certain threshold that you will say, yes, this is enough. I'm not going to mitigate risk anymore. How do I manage it? And in the context of that, we are putting together a system where we try and predict the future. Now, George Box came along and said that all models are wrong, only some are useful. If you extended that, all simulations are wrong, only some are useful. So if we can predict the future, that means future state of the system, and we have many predictions, we can then say, all right, what is the best policy that we implement here so that we are best able to manage a potential risk in the future? Because risk always deals with future.
Right.
So we are putting together a slightly different approach to risk, to what you talked about, risk mitigation. We talk about risk management with the idea of predicting the future. And this prediction we are doing using a system called system dynamics. So in the military, because the structure is so well put together, you're able to draw a cause and effect diagram as to who's connected to what, how it's connected, how information goes through. And so you're able to use this tool that has been put together by the social scientists called system dynamics to be able to say, this is how the system is going to behave or likely to behave. And that is something, if you're interested, I'd like to talk to you about offline sometime, just for the sake of talking, because your input, your 20 years experience may be valuable. You may just say, this is of no use to us, in which case, okay, that's good. Or you can say, hey, it will be of use to us if you did such and such.
Yeah. And I may have explained on the progressive collapse it not as clear as we're definitely not struggling so much with the how, it's the when to accept the risk.
Yes.
And how do I get, because I'll give you an example of one of our discussions recently is someone on the team is like, it's just, we should always apply the maximum progressive collapse mitigation because it's just insurance. And we always want to buy the insurance. And then, the counter on that is, well, if we did that for everything, like with wind load, why don't we make everything resist a tornado? We know how to do it, but we've come to a societal kind of a risk, even if it was indirectly done. And so we're definitely struggling more on the when to accept risk in a quantifiable way.
That's the same thing that we are talking about.
Yeah.
I'm just saying you simulate the future and say, okay, now let's look at that and take a calculated risk.
Yeah.
For example, the insurance company does it all the time. They gamble as to when, with actuary tables, and coming out and saying, "Oh yeah, so many people are going to die, so we'll make this much profit."
Mhm.
That's what you're looking at. You're looking at actuarial
Yes,
tables, actually. Same thing.
definitely. I never called it actuary, but that's for that project. That is the main, the crux that we're struggling with. How about that? It's
So anyway,
to
so
get a consensus. But yeah, I mean, if you can send me like details on it, I can see if our team, because I'm just one person on the team.
no, my interest is in chit-chatting with you. It's a chit-chat.
Okay, chit chat. Yeah,
Yeah. It's not
we
saying,
can chit chat then.
give me this, give me that. It's chit-chatting.
we can do that sometime.
Yeah.
You have
So
my
anyway,
email address.
so that's my two-penny thing that, as you were talking, it was going through my mind and said, aha, he's dealing with the same problem that we are talking about. We're
Yeah.
not dealing with buildings. We are dealing with policies that affect human beings.
Yeah. We intentionally don't call it policy, though. We call it criteria. But it's semantics. Because only certain people can make policy.
That's correct.
You have to be appointed to that.
You're right. Anyway, so thank you very much. So I've said my bit, Jason, back to you.
Can I ask one more question before we sign off?
Yeah, go ahead, Rodney.
Yeah, sorry, my meeting actually got rescheduled. I didn't know, but
Yeah.
I was wondering if the criteria you introduced today, the progressive risk, has it led to any like unintended consequences? Like, we don't want to deal with that, so we're just going to make way more of low-rise buildings, so we don't hit that 3-story threshold.
So that's there's two parts to that question. So, yes, one of our intentions in some, we'll say, difficult criteria is to help people decide to not do risky things. So when they're doing planning, hey, let's not build a 20-story building that's got, vulnerability because it's a 20-story building and we're kind of on, it's a potentially, let's say, a military target or something. We don't, so yeah, yes. Sorry, I lost my train of thought on that. What can you repeat your question? I apologize.
Yeah, sure. It was just has this criteria had unintended consequences, like forcing more low-rise buildings where, a high-rise might be more beneficial?
I remember the second part of my answer now. Sorry, and that is what. Yeah, so the criteria up until about a year ago applied. If you were doing a renovation project on a existing building, you had to take into account progressive collapse. If it was you were renovating it above a certain threshold. But it's really hard to mitigate progressive collapse risk to an existing building. So what was happening is we would do a design. The design would come back, it was going to cost more than the whole building was worth. But then because it's explicitly called for in the criteria, we have to get what's called an exemption, which goes through a giant bureaucratic process, which takes, that requires everybody to sign off. And then, it gets to somebody's desk and it's like, hey, we want to accept this risk. And they're like, well, I don't want to accept it. I'm not going to put my name on that. And so it delays the project forever. Maybe not forever, but for a long time. It costs lots of money and bureaucratic dealing with. So that's, one of our goals is to try to reduce bureaucratic stuff right now. That's so. Anyway, that's definitely an unintended consequence. We've said we don't require it on existing buildings anymore because we looked at the data and it was like, well, pretty much every single one, we spent all this money on design and then we wavered it. So we're just wasting time. So we eliminated that requirement last year, and now we're looking at it. Well, maybe 3 stories isn't the right. Maybe there's something else in the risk equation way we can, is there a difference between building a dormitory in Syria versus Oklahoma City as far as the risk? I mean, I would think so. So we want to, it might make more sense to have it in Syria, but maybe like on the Tinker Air Force Base in the middle of the base, who's driving a 5,000-pound bomb somehow onto the base into the right location? It's not the same risk. So, but we're not there yet. So
Perfect. Thank you. Jason, I'll let you take over again.
It's okay. Well, I really appreciate Kevin joining us today. It was great hearing about your work again. I know there's a few things I'd like to ask, but we're at 1 p.m., our time. And in the future, if Farouk ever contacts you again, definitely please add me on to that contact. I'd like to always be here when you have another speaking. And then hopefully I'll also get to hear one of your seminars too for training purposes later on in life. So I know I missed the one I think you gave a month or so ago, right? On construction.
yeah, I did one. You can still watch it if you want.
Oh, okay. It was
This won't be
recorded.
live. You can't answer my quizzes.
Well, again, very appreciated seeing you again. Like Kevin said,
Yeah.
he hired me a long time ago, in January 2011, and yes, I almost hit with my car. Way back then. That is a true story.
I told you I was only going to do one embarrassing story. I had more.